Have you ever stopped to think about how your body can take a meal, a sandwich or a cookie, and turn it into energy in just a matter of minutes? Well, it's not magic, it's chemistry. But it's chemistry moving at a speed that would otherwise be completely impossible. So today we're going to dive into the microscopic world of enzymes. These are the biological catalysts that literally make life happen.
All right, so here's the plan. We'll start with a little sugar-coated mystery, then we'll meet life's ultimate catalysts and take a look at their anatomy. After that, we're going to uncover the secret to their incredible speed before we see how enzymes shape our world every single day.
Okay, so let's kick things off with a puzzle. At the very heart of all life is the need to use energy from our environment, right? And for a lot of us, that energy comes in the form of sugar. But sugar presents this really fascinating problem. Seriously, think about this for a second. That cookie left on your kitchen counter, it seems perfectly stable. It'll just sit there. But if you eat it, your body almost instantly starts breaking it down for energy. So what is the big difference between the cookie on the counter and the cookie in your stomach? The difference in speed here is just staggering. A bag of sugar can sit on your shelf for years without really changing. Now, chemically, it actually wants to break down into carbon dioxide and water, but that reaction on its own is incredibly slow. But in your body, that very same sugar releases its energy in seconds. This incredible, mind-blowing difference in speed is thanks to one thing, and the answer is enzymes. They're the entire reason life can happen on a timescale that's actually useful. Without them, the chemical reactions we need to survive would just be way, way too slow. For a long time, scientists were totally stumped by this. Back in the 1850s, Louis Pasteur thought these reactions were caused by some kind of mysterious ferments that were inseparable from living cells. This idea was called vitalism, the belief that you needed a special life force. But as it turns out, the answer was something you could actually touch and study. Our modern understanding was really built step by step. In 1897, a guy named Edward Buchner showed that these so-called ferments, which he called enzymes, were just molecules, not some kind of life force. Then, fast forward to 1926, James Sumner proved that enzymes are actually proteins. And then in the 1930s, J.B.S. Haldane offered this brilliant insight into how they might actually work their magic. Buchner's experiment was the real turning point. I mean, by using just yeast extracts with no living cells at all to ferment sugar, he proved something totally revolutionary. The catalysts of life weren't some mystical force. No, they were physical molecules that you could study and understand. Okay, so if enzymes are physical molecules, what exactly are they made of? Let's break down the components that give them this extraordinary power. So the fundamental building block is a protein, and it's the specific, complex, three-dimensional shape of that protein that is absolutely essential for what it does. It creates this perfectly tailored little pocket. But for a lot of enzymes, the protein alone just isn't enough. They need a partner to get the job done. When we're talking about just the protein part of an enzyme, before it's ready to work, we call it an apoenzyme. You can think of it like the main engine of a car, but it's currently turned off. It's inactive. Now, that partner it needs, that's called a cofactor. This can be something simple like an iron or a magnesium ion, or it can be a more complex organic molecule, which we call a coenzyme. And get this, many coenzymes are actually derived from the vitamins in our diet. For instance, vitamin B3 is crucial for making NAD, a coenzyme that's vital for our metabolism. And when you put them both together, the apoenzyme and its cofactor, you get the complete, fully active unit. And this is called the Holoenzyme. It's the whole shebang ready to go out there and catalyze a reaction. So how does this fully active enzyme, this holoenzyme, make reactions go thousands or even millions of times faster? Well, the secret lies in overcoming something called the activation energy barrier. So every enzyme has this special pocket or groove, and it's called the active site. This is where all the magic happens. The molecule that the enzyme works on, we call that the substrate, fits right into this site, kind of like a key into a lock. Now, for any chemical reaction to happen, even one that wants to happen, the starting molecules need a little jolt of energy to get things started. Think of it like needing to push a huge boulder up a small hill before it can roll all the way down a much bigger one. That initial push, that's the activation energy. And the height of that energy hill is what determines the speed of the reaction. A really high hill means only a few molecules have enough energy to make it over at any given time, which, you guessed it, means a very slow reaction.
But a low hill, that means the reaction can happen very, very quickly.
So, how in the world do enzymes lower that hill? Haldane's early insight was just brilliant. He imagined the enzyme as like a lock, and the substrate is like a key that doesn't fit perfectly. As the enzyme grabs onto it, it puts a strain on the substrate, which makes it easier for it to react. We now call this the induced fit model. The enzyme actually changes its shape slightly to grip the substrate, stressing its chemical bonds. So the best way to think about it is this. An uncatalyzed reaction has to climb this huge mountain of activation energy. An enzyme doesn't get rid of the mountain. Instead, it basically provides a tunnel right through it. It creates a brand new, much lower energy pathway for the reaction to follow. A shortcut. Okay, but this isn't just some abstract biochemistry lesson. Understanding how enzymes work has a massive, massive impact on our daily lives, from the medicine we take to the food we eat. Think about it. Doctors can diagnose illnesses just by measuring the enzyme levels in your blood. A lot of the most effective drugs work by blocking the active sites of specific enzymes. And they're used all over the place in food processing to do things like make cheese or tenderize meat. They are powerful tools in the chemical industry. They're literally everywhere.
So when you get right down to it, enzymes are nature's perfect little microscopic machines. They've been honed by millions of years of evolution for incredible speed and precision. And that leaves us with this one final fascinating thought. If we can fully master their secrets, what new problems could we solve by designing and building our own custom enzymes from scratch?